So as I've mentioned to you, there is one more topic that we have to look at. It wasn't on the AP exam, but colleges will sort of expect that if you've taken calculus, you've seen this topic. So we're going to do one last thing. We're going to go nice and slow. We're going to spread this out over 3 days. I've taught this in 1 day or 2 days in the past, so we're going to go nice and slow. But I do need to show you this. I'll keep the homework relatively small. But let's finish this up. We're going to take a look at section 7.2 about a technique of integration called integration by parts. And really what you need to know about this is finally our product rule for integrals. This is our product rule for integrals. Now, even though I haven't yet taught you the product rule for integrals, there are some products that I could give you that you could already handle. So I'm going to say some products we could already do. For example, if I ask you to do the integral of x squared times the sine of x cubed dx, or if I ask you to do the integral of x squared e to the x cubed or something like that, you could handle those products because those are just u substitutions. You'd make u, actually in both cases, you'd make u x cubed, du is 3x squared, stick a 3 inside, 1/3 outside, and go from there. Just because I'm about to teach you a new product rule doesn't mean you're going to use it on every single product that you get. If you get something like this that we could have handled before, the only way you could deal with those is by using u substitution, not the new method I'm about to show you. However, some products you can't handle yet. Things like, for example, the integral of x times the sine of x dx, or maybe something like the integral of x squared times e to the x to the fourth. Make u, I don't even know because its derivative isn't showing up. Over here, I would want to make u x to the fourth, but then its derivative is 4x cubed. I'd be okay if this was an x cubed, but it's an x squared, so that's not going to work. I need a new method for dealing with this. Again, this method I'm about to teach you is called integration by parts. And it comes from what we know about the derivative of a product. I'm going to start by saying the derivative of u times v equals, well, my product rule says first times derivative of the second plus second times derivative of the first. I'm going to say u times dv dx plus v times du dx. That's just my regular product rule for derivatives. Again, what I'm trying to do here is derive this formula we're about to use for the product rule for integrals. Rather than writing it in this notation, I'm going to go switch to the Leibniz notation for derivatives using those differentials, because that largely is the notation that we use when we're dealing with integrals. So instead of writing it like that, well, actually, I'll keep it like this. The derivative of u times v equals, I'm just going to say u dv plus v du. And I'm going to go integrate both sides. I'm going to go integrate the derivative of u times v dx. And on the other side, I'm going to go integrate u dv. And I'm going to integrate v du. Well, on the left, I know if I integrate a derivative, those things cancel. So really, I'm just getting u times v. And on the other side, there actually isn't anything I can do. I'm just going to say the integral of u dv plus the integral of v du. I'm going to move things around a little bit. I'm going to subtract the integral of v du from both sides. I'm going to switch sides a little bit, and I'm going to get the integral of u. Oh, you can't see that. Let me try that again. You're going to get the integral of u dv equals u times v minus the integral of v du. And this is our formula for integration by parts, which I don't expect you to be able to look at and really have a clue what this is telling us. The rest of today, I'm just going to show you some examples of how this really will be the product rule for integrals and will let us deal with things like this problem or that problem over there. First example I'd like to take a look at. I want to do the integral of x times the sine of x dx. Before I try to get into this, just to kind of talk through what this formula is saying. This formula is saying if I want to integrate one function times, not really another function, but times the derivative of another function, I'll do the first function times the second function, minus the integral of the second function times the derivative of the first. Okay, so I need to try to get a u and a dv for my product. How about I just say x is my u, and my dv, the derivative of something else, is that whole other piece, that sine x dx. I'm going to go write out a little bit of work on the side. I'm going to say that u equals x, and I'm going to say that dv equals the sine of x dx. Well, according to my formula, I need to do u times v. I've got u, I don't have v, minus the integral of v du. I still don't have v, and I also don't have du. I'm going to go and calculate a couple things. If I know that u is x, its derivative, du, is just, if we're in Leibniz's notation, what's the derivative of x? Well, just 1 dx. I'm doing a derivative to get that. Now, I have dv. If I want to figure out what v is, well, dv is the derivative of v, so v should be the integral of dv. I need to do the integral of the sine of x dx. I think I'm going to get negative cosine x. And yeah, I know there's a plus c. I'm going to ignore that for right now. According to my formula, this integral over here, x times the sine of x dx, should equal u times v, well, u times v, minus the integral of v du. Okay, so according to that formula, this should be u times v, x times negative cosine x, again, that's my u, times v, let me fix that, u times v, minus the integral of v du, so that's minus the integral of negative cosine x dx, that's my v, that's my du. Let me clean this up. This is going to equal negative x cosine x. I'll turn that double negative stuff into a plus, so plus the integral of the cosine of x dx. Well, I still have an integral in my problem, but this integral is so much easier than the original integral. That's the integral of the cosine of x dx, just the sine of x. So I'm going to say negative x cosine x plus the sine of x plus a constant. And I just did my first product rule for integrals example. The integral of x times the sine of x dx is negative x cosine x plus sine x plus c. In every problem that we have a product, we're going to call one of the pieces of our product u, and the other piece of our product, along with the dx, my dv. I'm going to write those out on the side. Then I'm going to go and calculate two other things. I've got u, I can calculate du, its derivative. I've got dv, I can calculate v, the integral, and get your v. According to my formula, I need to do u times v minus the integral of v times du. So I'm going to write that stuff out. I still have an integral, but the integral is an easier one that I can deal with, and I'm going to get that. Let's take a look at a couple more. Let's see. Okay. It's on the screen now. Let's take a look at the integral of x times the natural log of x dx. I'm going to go and I'm going to do my integration by parts formula. I'm going to call this u. I'm going to call the other part dv, so I'm going to go write that out. U is x, and dv is the natural log of x dx. Du, that's really easy. Derivative of x is just 1 dx, so I'll fill that in over there. V is the integral of the natural log of x dx. Oh. I know how to do the derivative of the natural log of x, but I don't know how to do the integral of the natural log of x dx yet. Not really sure. Can't do this. So, you know what? Rather than trying to do the problem as x times the natural log of x, multiplication is commutative. I can just switch the order. My original problem, I could say it's the natural log of x times x dx. It's the same thing. Maybe if I switch the order, it'll make this one work. If we try it like this, I could say that u equals the natural log of x, and dv equals x dx. Du, I can certainly do the derivative of the natural log of x. That's just 1 over x dx. And as for v, that's the integral of x dx. Well, I can do the integral of x dx. I'm going to get x squared over 2 plus a constant, but I'm going to ignore the constants for now. And now I can go and use my formula that says I need to do u times v minus the integral of v du. This is going to equal the natural log of x times x squared over 2 minus the integral of, okay, let's see, x squared over 2 times 1 over x dx. This looks ugly, but I can simplify that. First of all, just for fun, I'm going to move the x squared over 2 out front. X squared over 2 times the natural log of x, or a 1/2, or whatever. Over 2, just so you see the simplifying, I'm going to write this as x squared over 2x dx. I can move that 2 in the denominator out front as a 1/2 over there. So I'm going to say minus 1/2 times the integral. Well, x squared over x, that's just x. And I'm going to get this problem. Again, I still have an integral, but it's a much easier integral to deal with. So I'm going to go 1/2 x squared times the natural log of x minus 1/2 times x squared over 2. And then I'll stick my constant at the end. Clean this up and say 1/2 x squared ln x minus 1/4 x squared plus a constant. By the way, if you don't trust any of this stuff, go and find your derivative of this. If you do, you're going to get x times the natural log of x back. What this problem, I hope, showed you, though, is that it really matters which part of the product I make my u and which part I make, whoops, you can't see that, which part am I going to make my u and what part am I going to make my dv. Because we need to make sure that the dv is something that I can easily integrate, and u should be something I can find a nice derivative of. Well, I've got a little trick, so we don't have to just try something, run into a problem, and then try switching things. There's a little trick that I learned that will let us figure out right away which one should be u and which one should be dv. So I'm going to call this next piece, how do we figure out u and dv? And like a lot of the other things I've showed you this year, this is a trick I learned from my high school calculus teacher. I'm going to write down 5 letters, L-I-A-T-E. And he pronounced this liate. Here's what this acronym stands for. L stands for logarithmic. These are different types of functions, by the way. I stands for inverse trig, arc sine, arc cosine. A stands for algebraic. Things like polynomials, radicals, things like that. T, trigonometric. And the E, exponential. What I'm going to do with this problem, actually what I'm going to do with this acronym rather, is I'm going to look at the two types of functions that I have in my integral, and I'm going to put little check marks above the two types that we have. I'm going to put little check marks above the two types we have. The first letter that has a check mark above it ends up being U. The first letter, as we read from left to right, will be U, and the second letter will be dV. So let me show you how to use this. If we're going to go do the integral of x times the natural log of x dx, like the problem we just did at the top, I'm going to write out that little acronym, L-I-A-T-E, liate. I've got an x. I'd call that an algebraic function. Put a check mark above the A. Natural log of x, that's certainly a logarithmic function. I'm going to put a check above the L. The first letter, going from left to right, is my U, and the second is my dV. According to this little acronym, I'm going to make my U the natural log of x, then I'm going to make my dV x dx. And if you go back to when we did that problem, yeah, that's exactly what happened. I made U x dV was natural log of x dx. That didn't work. When I switched the order and made my U the natural log of x and dV x dx, then it did work. I have two more examples to show you. Oops. Okay, we're going to take a look at the integral. Example, I want to do the integral of x times e to the x dx. The integral of x times e to the x dx. L-I-A-T-E. X is an algebraic function. E to the x is an exponential function. I'm going to make my u the algebraic part, so I'm going to make ux, and I'm going to make my dv e to the x dx. Du, the derivative of x, that's just 1 dx. V is the integral of e to the x dx. I know that's just e to the x. By the way, the reason this whole little acronym thing works is as we move through this acronym from left to right, the types of functions furthest to the right are the functions that are the easiest ones to integrate. I can't think of an easier function to integrate than e to the x. Trig functions are also pretty easy. Sine becomes a cosine, cosine becomes a sine, with various combinations of positives and negatives and all those things. Then we have the algebraic functions. Polynomials aren't that hard. Inverse trig, though, we don't know how to integrate those yet. Certainly don't know how to integrate a natural log. As we move through this, the later things are the things that are easier to integrate, and that's what I'm making dv, the thing that I am integrating. According to my formula, u times v minus the integral of v du. I'm going to do x, e to the x, minus the integral of e to the x dx. Again, there's an integral left, but that's okay. It's an easy one. This will give me x e to the x minus integral of e to the x is e to the x plus a constant. I want to show you one variation on integration by parts. Our next two classes will all be about variations on this, but today I really just kind of want to focus largely on the basics. Just one variation. I'd like to take a look at the integral of x squared cosine x dx. Go write out your LIATE, figure out what's u and what's your dv. See, I'm going to go make u x squared I'm going to make my dv the cosine of x dx. Du, derivative of x squared, is 2x dx. V, the integral of cosine x, sine x. So this times this, minus that times that. I am going to get x squared sine x minus the integral of, let's see, 2x sine x dx. And I'm going to go and move that 2 out front, and I'm going to get x squared sine x minus 2 times the integral of x sine x dx. So now all I have to do is integrate that thing. However, it's a product, and it's a product where product rule isn't real, not product rule, U substitution isn't going to get me anywhere. I need to go use this product rule for integrals, this integration by parts. Again. We'll call this a repeated integration by parts problem. Even though I have to use it again, this will be a little nicer than the original problem, because the original problem was an x squared times a trig function. Now it's just x times a trig function. So if this pattern continues, I shouldn't have any x's out front before my trig function in the next step. Well, here we go. Liate A and T. I'm going to say that u is x. I'm going to say dv is the sine of x dx. Du, derivative of x, is 1 dx, or just dx. V, integral of sine x, make sure it's negative cosine x. I'm going to go do u times v minus the integral of v du. Oh good, those birds sure are loud out there. Let's see, we've got x squared sine x minus 2 times, okay, u times v, so x times negative cosine x, why don't I just write that as negative x cosine x, minus the integral of v du, so minus the integral of negative cosine x dx. I'm going to clean that up. Let me move this up a little bit. I'm going to get x squared sine x. I'll leave my 2 out front for now. I'll distribute a little later. Negative x cosine x. The double negatives will become a plus, so plus the integral of the cosine of x dx. And yeah, my prediction was correct. I still have an integral, but now it's a much easier integral. It's no longer a product. There's no algebraic part. It's just integrating the cosine of x, which I know is just the sine of x. So I'm going to get x squared sine x minus 2 times negative x cosine x plus sine x. And I might as well add my plus c at the very end. I'm just going to go and distribute that negative 2, and I'm going to get x squared sine x plus 2x cosine x minus 2 sine x plus a constant. And that's repeated integration by parts if we do our integration by parts, but the integral we're left with still looks like a product. We need to use integration by parts again. Next time we're going to look at a bunch of other variations on this, but that's where I want to stop for today.